Okay, welcome to our weather discussion. This will be the last one of the term, unless, as Pete pointed out when I came down this morning, unless something really interesting gets brewed up for next Friday. So, you know, if there's something interesting happening, and I think the level of urgency would have to be falling frozen precipitation for me. If that's not in the cards, I'm likely to be spending my time doing something else. That doesn't mean you can't come down here and do a discussion if you find something that's that you purport to be as interesting as that, and worthy, therefore, of discussion. It won't be in my wheelhouse that week. But finally, at the end of the term, we actually get a snow event to talk about today, so that'll be kind of fun. That's one aspect of the discussion today. Another is evident in this week-long satellite movie that Pete's made for us, and I'll point that out in a minute. The incredible cold pool that was over central Canada all week long was just remarkable. I don't know if I've seen temperatures, actual observations. We'll look at them in the Super Pete movie. Super Pete the movie. Imagine that. We'll look at them in the movie. There are some actual odds in the minus 46 to minus 48 range again. Real radius on. I mean, at 500 millibars. Unbelievable. I've never seen minus 50 at 500 millibars anywhere. But we got really close in early December this week. And then there's this interesting thing on the edge of this view, this subtropical disturbance that maybe started out as an extratropical disturbance. It ends up warm core at the end. We're going to take a look at that. Not with a sense that I know how it worked, but just to kind of look at the glory of this beast and try and see, you know, what kind of things we can discern at a quick glance. So we're looking at a whole week's worth of satellite movies. I think these are, I always say this is every hour or so, or maybe
every half hour.
Okay, every half hour. Since the beginning of this would be a week ago today, the 2nd, and we're going to go all the way to the 9th. So you'll see a few things. Here's one of the things of great interest. Watch the region in central Canada. And it's a huge part of the country that is, especially in the early part of the week. Now, late in the week, it kind of goes away. This is the enhanced infrared. And so when we get back to the beginning of the week, when you see these greens and whatnot, that means that the cloud-free surface is as cold as the tops of these convective-type clouds that are coming in out of the subtropics. So this is really, really cold air that's sitting here over the surface and at 500 mil, upper half of the atmosphere anyway. And you can really see it. It looks like Lake Winnipeg is frozen, and you can see why that's worthy of mention. It stays blue. But you won't see that when the low-level stratus clouds move away from Lake Michigan. It shows a beautiful diurnal cycle starting right about now. So here the lake is warm, the land is cold. It's overnight. That's just the last night. But you'll see earlier in the week when we had some clear skies and some kind of nice days, a nice diurnal cycle. So the lake is warmer than the land, and then during the day it goes the other way around, or gets about even and back and forth. Pretty nice. So you can see all kinds of interesting structures related to the thermal field in this kind of an image. And it's especially noteworthy this week, as we'll point out with some real observations in just a minute, how cold it was over most of central Canada this week. It's just astounding. And the circulation feature that's associated with it is also a noteworthy feature. You can't miss it. Okay? You just can't miss it. Now that's one thing. Then there's stuff brewing here just north of the Caribbean. This cloud mass looks like not too much here in the first part of the week, but then it starts to gain some circulation. We'll see what happens with this thing in some different portrayals. But there's sea level pressure gets down into the 950 range associated with this thing, while it develops, I think, quite obvious frontal structure, especially a strong warm frontal structure. That's off the map. It's sort of more over here. And then it spins little disturbances toward Iberia, toward North Africa, all at the end of the week into the forecast of the weekend. So it's a really weather-generating feature in the central, maybe subtropical Atlantic that moves into the mid-latitude Atlantic, southern mid-latitude Atlantic, by the end of the week. So not a good week for, you know, trying some of these crazy stunts that people pull, like rowing a boat across the Atlantic from, you know, from Lisbon or something like that. This wouldn't have been a good week to do that. The weather is really wild in the central Atlantic. So that's one feature that we'll talk about a little bit as well. And then we'll go in just now, Pete, if we could, certainly the snow event, but we'll zoom in on that in the last bit. Let's go to the Pacific satellite image, if we could. maybe we'll not do the whole week, we'll just do the last, part of the morning here or something. So this is today. A nice disturbance coming into the Pacific Northwest, presumably in sort of strong westerly flow. We'll see how that lines up with our 500 millibar maps. This is a time when, in this portion of the ITCZ, it's a little more active than it's been at certain other weeks this semester, so that's kind of interesting. But then a bald spot all the way from the date line well to the west along that same region. And then a couple of really big storms up here in the Bering Sea, and we're catching this one late in its life cycle, and we'll see some evidence of some of the structure associated with that in other core trails as well. Yesterday in 452, we were talking about a disturbance that was up here at the far northwestern coast of British Columbia, southeastern coast of Alaska. One still sees the circulation rotating around in there, but not as obviously as yesterday. Yesterday was quite dramatic. And the air we found was about minus 38, minus 39 at 500. So pretty cold, low stratification, and a superimposed circulation on top of it really produced a beautiful little small-scale cyclone there that's now kind of broken up a little bit compared to what we saw yesterday. Okay, so that's the broad view over the continental U.S. and adjacent waters, and then parts of Canada as well. Let's go through some of our, let's take a close-up view of the infrared over the continental U.S. Close-up meaning in time feet. We'll just look at the current one over the United States. So this will only be the last several hours. And it's already too late to see the development of this feature. Maybe we'll have to go back to the weeks-long one. Yeah, could we do that, Pete?
Sure.
And then we'll just intercept it.
Yeah, I can scroll it too.
Yeah, let's get to about maybe early on the 6th or something. And then we'll stop when we get there. We can stop right about here and a little bit further on. Okay, right about here would be good. So this is near the end of the day, December 5th, and today's the 9th, so we were looking at an event that was kind of, if we move forward, we're going to see the circulation associated with the feature of interest come off the Pacific coast. So there it is right there. And stop again if we could, just to make sure we're on track. Yeah, I think this is the right thing. And then that feature has just made its way onshore in Southern California. Let's go again. And it seems to have disappeared. However, there it is. Pretty obviously a nice little circulation feature right over the Four Corners area. Only the northern portion of it remains, at least in the high clouds, as we get into midday on the 8th. And this is the feature of interest that is currently exiting, but over the course of last night and the morning gave us a pretty good snow. So let's step through this if we could. So really interesting. It's not hard to rediscover the circulation if you kind of click a little faster than that. You can see a counterclockwise rotation, and notice the clouds continue to just they go through a phase of sort of widespread and well-developed, and then it kind of decayed, and then it got nicely well-developed right over us, and now we're at 16Z, so you can see here in Madison, the higher cloud now to our north and east, and unsurprisingly, not as precipitating quite as hot as it was earlier this morning, and so, if at all. And so this very small-scale feature just absolutely had our city as a target, and it just came right over us, and you couldn't have asked for a better situation. Look at how small-scale the thing remains throughout its short life cycle, and the forecast for this, you can't see in the satellite course, but the forecast for this is that it just dissipates later on to the east here during the day. It completely disappears. So it was short-lived, reasonably intense when it came through, and just perfectly targeted for Madison. So whether you like this kind of weather or not, you have to admit this was a matter of perfect targeting. And then there's nothing particularly upstream of it in the near term, but by the end of the weekend there's something coming next. So let's take a look at the radar, if we could, Pete. Oh, isn't that nice? Look at that. So some of this there's a transition between snow and rain, because we were at 33 degrees and snowing. So further to the south, some of the reflectivities here in northern Indiana, undoubtedly at least mixed rain and snow. In fact, sometimes snowflakes with water on top of them give you the big reflectivity signal, even though they might still fall mostly as snow. But this is the band of precipitation, and it was fairly intense, as we all know, several hours ago. This started at 15Z, so 9 o'clock, just about when it was winding down here. If we had it just a little bit longer, we would have seen a really heavier snow from about 4 a.m., 5 a.m., all the way through about 10 a.m. And so you can see this is all gone, and there's absolutely nothing left of it. This is a small-scale feature, and we're going to try and diagnose what was it that drove this thing, not only while it was over us, but maybe a little bit of its history, where it was coming from. Okay, so that's what we hope to do with that. And then up in the Pacific Northwest, open cellular convection coming on shore in the state of Washington, and then it gets a little bit more filled in as the day progresses. So probably the next better organized weather system than just the isolated showers that develop, because you have cold air aloft over the relatively warm water, and that reduces the stability, and that's a common precipitation element in Seattle. And in fact, when I was there, when I first got there especially, I was shocked by how much of the precipitation falls after the cold front comes through in a regular cyclone. It's almost most of it, because it's all that open cellular convection under the cold pool aloft. Okay, so those are a couple of things we'll keep our eyes out for when we go to the upper level charts, which we'll do next. Well, actually, let's look at the surface ops first, Pete, but mostly in our region, because that's about where things are interesting. Patrick, yesterday in our class, we'll talk a little bit about this cold outbreak that we had this week, this cold front that came through earlier in the week. And Patrick found some observations on, was it the 5th, Patrick? I think it was in the 5th and 6th. What was the coldest temperature we found? Minus 37, was it? Still air temperature in a town called Nowheresville, North Dakota, or whatever it's called. I forget what it's called. Yeah. Minus 37. And the wind chill was minus 58, was it, or 59?
57.
57, okay, yeah, unbelievably cold. Okay, so here's some current obs, or reasonably current. Look at how close we are to the rain. It's raining in Rockford, it's raining in Chicago, it's moderate rain in Gary, moderate snow in Milwaukee, and we are light snow at the hour this map was made. Some light snow also to the southeast of Minneapolis. And then fog everywhere to the south and west of us, a little bit of snow in northern Iowa. And that's it for the snow, none of it in Michigan. And whatever precipitation is falling in Indiana is, and maybe between stations, is certainly going to be of the liquid variety, because it's raining in the northern part of the state, and it's much warmer to the south. It's 47 near Indianapolis, 42 actually in the city, 50 down at the border between, I don't know what that is. I have a friend who's from that town. Can't remember it off the top of my head. Anyway, on the border of Kentucky and Indiana. So pretty warm to the south, and barely cold enough to snow everywhere, actually, where it was snowing. It's only, a few places that are below 30. So it's pretty, look at this. Freezing rain with 19 over 18. How's that happen? What in the world must the vertical structure look like at this station? Freezing rain with a 19-degree temperature and 18-degree dew point. Wow, that's wild. Okay, so that's all I wanted to see from the surface ops. Now let's take a look at our upper level ops. Oh, one last thing. Sorry, Pete.
Sorry.
Trying to discern a circulation here. Easterly flow over us, northeasterly over Iowa, then northwesterly. Maybe the circulation comes around, let's see, then the southeasterlies, or southwesterlies in St. Louis. Somewhere in here is the center of the circulation, and in western Illinois. And look at the pressures, 1,018.1, 1,019.5, 1,017.7. That looks like the lowest pressure on the map. So this thing, as Patrick pointed out yesterday in our discussion, is almost 6 millibars higher than standard sea level pressure as a circulation feature. And yet there were not cancellations, but delays. I waited 5 times longer than normal for the bus today, as probably everybody else did who takes the bus. A non-existent low pressure center hit at the right time and delivered a pretty sizable impact. So, you don't have to get down to 950 millibars to have an impact. This one here was only about 1,017.7 at the time when we were getting kind of blasted with a heavy snow event. Okay, so that's pretty cool. Let's go to the upper level charts. Let's start at 500 millibars, Pete. And we'll do just the image now, but in the future we'll go to the Super Pete movie. So here's the 7 a.m. Forecast, observation, sorry. Somewhat understated on this map. The gradient of geopotential here in northern Missouri is quite strong. So you get 70 knots at Dodge City and 50 at Lincoln, Illinois. So that's a pretty strong 500 millibar jet max. And then the winds to the south are pretty strong. They're in the 60 to 70 knot range broadly. So one gets the impression just from the initial look at this map that there's a broad west-southwesterly flow all the way from the Baja California to the Middle Atlantic, to the south of a superimposed wave that comes right along with it. It's kind of moving really quickly, and that accounts for the short duration of our event, looks like. We want to see what that looks like at various other levels. So that's the first thing I want to show, is that one expects a decent vorticity maxima right over the state of Iowa, given this shape at 500 millibars. There's not only strong curvature, but there's decent cyclonic shear. The winds are strongest right where the hand is, much weaker in central and northern Iowa. So you have shear vorticity added to the curvature vorticity. Let's go to the, before we go anywhere else, Pete, let's go to the 12Z NAM grid. And I'm using, and we'll go to the 0 hour 500 millibar. I'm using this just because it gives you an unspeckled view, a sort of poorly resolved view of the 500 millibar vorticity. But this is the same geopotential height contours we just saw. And then look at this vorticity maxima. It's in that purple, 4 times the Coriolis parameter. So this is a really impressive upper level low, okay? Even though it's a very small scale, it occupies nearly the entire state of Iowa, but only the state of Iowa. So that's pretty interesting. And so I'm going to keep my pointer right there, not at the maximum, but at a point where I think the gradient is about the strongest, right there. And let's go to the surface map at 0 hour, and we can see the thickness field implied by, the thermal wind field implied by the thickness field. So here's the 540 decameter line, 546. So the thermal wind is really strong right here in southeast Iowa and northern Missouri. Maximum vorticity gradient right about where my 2 fingers are. And so we have strong PVA by the thermal wind over northern Illinois, southern Wisconsin at 12Z. And that's exactly where we saw that cloud in the infrared really start to grow again. Remember, it went through that period of looked a little better when it was further to the west, then decayed a little bit in the satellite presentation, then showed up nicely as sort of a croissant-shaped cloud mass right in here. That's exactly where it should if it's following the rules. And of course, it has no opportunity to disallow, to disobey those rules. So of course it does. And 1,016 millibars, just about what we have now. Things already weakening. This is a forecast or an analysis, and we're several hours out ahead of it. So really strong thermal wind, microscale region where it's strong, but it's exactly in the same place as the strong vorticity. So the PVA by the thermal wind is really strong right there. Let's verify that as best we can. We'll go to the real-time omega plots. That's the first panel. And then let's, this is from 0Z, so let's go here. This will be the total omega at the same time. The yellows are ascent, the blues are descent, and this is the solution of the QG omega equation, but from last night's 0Z run. And this is 4 decameter, decipascal per second, it's about 4 centimeters per second updraft, right over the nose of Iowa, exactly where one expected it from that simple way of looking at it. And if you remember the vorticity maxima being right in Iowa, actually bleeding into Missouri, and the dotted lines here are 500 to 900 thickness. So that gives you an indication of the lower tropospheric thermal wind. And it's a beautiful couplet straddling the vorticity maxima, just exactly as the textbooks say it should be. And that's what you get from the GFS if you invert the omega equation. Okay? And let's split this into shear and curvature if we can, Pete. Just go back on this page. So the scrolling up. So first of all, we should show the Sutcliffe, because that's really what this partition will be. So this is the approximation by just PVA by the thermal wind. It looks almost exactly like the total omega equation. So that's a really nice verification that that's the story for this event. Now we can split this into what kind of vorticity, shear vorticity or curvature vorticity that's being affected by the thermal wind. The sum should give you this. So let's go to the shear first. That's like 25% of the total. It's a small fraction of it. So the shear, though it's obviously there, is not the main player. And let's look at the curvature then. One expects it ought to be 3/4 of it. It looks like it is. It's probably somewhere lost in a contour interval here, but it's close to 3/4 of it on both pieces of the couplet. So it's the curvature in the flow that's really driving the snowfall this morning, not so much the shear, although they both contribute in a non-negligible way. And then we'll say a little bit more about this thing in the tropical Atlantic, but there's just a picture of just one component. This is just a curvature vorticity advection by the thermal wind at the same time for this disturbance. Strong ascent to the north, strong descent to the south. But I won't do any more of the QG omega part of that. Okay. Oh, okay, Pete, can we go back to our upper 500 millibar maps? And let's do a movie now. Of the super peak. And then stop it so we can step through. So let's go back to the beginning if we could. So this is last week at this time, a 12Z map from last Friday. Pretty decent disturbance hugging the British Columbia coast, about to crash into sort of Northern California a day or two later. Broadly speaking, otherwise, pretty broad westerly, southwesterly flow across the whole continent, which made us feel a little bit warm at parts of the weekend, last weekend. But cold air was lurking. Minus 48 up in the archipelago at whatever the station is right there, and that's the coldest in the whole map, by far. Look at the state of Alaska, minus 23 at Nome and minus 48 over the archipelago. That's not good for us. That tends to make us cold in the long run. So let's step forward, and I want you to see what happens to this giant cyclonic circulation begins to take shape, centered sort of on the western shores of Hudson Bay. We can keep going. There's our upper low coming across. Now, look at this. 4855 decameter, actually meter heights over the southwestern part of Hudson Bay. This whole upper low is just about cut off, and it's rung by a really strong temperature contrast, especially on its western side, where you have 115 knot wind right there in the Yukon territory. Minus 46, minus 48. Let's keep going. Oh, go back. Minus 50 at Churchill, Manitoba, at 500 millibars. That's the first time I have ever, in my almost 60 years of life, seen minus 50 at 500 millibars. Okay, so I didn't even notice it this morning preparing. Minus 50 at Churchill. I'm guessing that's way out of line, climatologically. That is bitterly cold, okay? And then notice how this is all cut off beautifully over the whole country of Canada, with the exception of British Columbia and the Yukon. Let's keep going. Churchill just froze out. They don't even have an ob the next time because no one can get to work. Let's see what happens next. The whole day, the whole week's off in Churchill and Manitoba, and also in the farther Northwest Territories. Keep on going. I'm back at work at Churchill. It's a little warmer, minus 47. And so you can see this broad cutoff feature. This is like the great blue spot, you know, and blue because it's so cold. But look at strong 50 knot easterlies on the northern side of this thing over the archipelago. 40 knots in the strait. Incredible circulation anomaly. And here comes our upper level feature. This is now 0Z on December 7th. Let's keep stepping forward. We were looking at it right about the next time. We were looking at it like this yesterday. And my thought was, we've got this kind of broad, maybe saggy confluence zone right here. This feature maybe gets put through the meat grinder and gets stretched right out. It doesn't turn into anything. And that was I did the current weather and Patrick did the forecast. So when I said that as my supposition, Patrick said, oh, I take issue, watch when you see this 500 millibar vorticity feature, and he was dead on. It was exactly right. So this thing survived through maybe it's because the confluence zone is really confined to the northern portion, and then this thing's just being ushered along by this really strong southwesterly flow. Look at how everything's greater than 50 or 60 knots over the whole southwestern U.S. and the southeastern U.S. Okay, and then one more is, two more gets us to where we are, so it's a little stronger upper wave. And it's not any longer such a strong cutoff circulation feature sitting over the largest part of Canada. So that's kind of gone away, but that was a remarkable week and easy to miss it. In fact, I missed the minus 50 at Churchill. I don't know how I did that, but I did. I think I'll have to go and look at the sounding to make sure that it's actually minus 50 and not minus 49.9. Because that happened at SeaTac. The only time that it got to 100 degrees when I was there, it was 99.9. So they round up, but it wasn't 100. But they did it last June, so that's okay. They broke that record. Okay, so that's probably enough on our system for the snow. First snow of the year is always exciting, especially when it has nice diagnosable signals. They don't always come that way, and this one did, so that's nice. Can we go to the Alicia maps? I've got it set up for the Atlantic. So starting at 0Z on the 5th of December, let's just page through these or click through them, Pete. It's this region of low pressure, 1,008 millibars, just off the Antilles. Watch what happens here. So a little bit more development, back and forth, 1,004 stays in there. That's a little bit more, maybe 1,006. They do them every two, don't they? So it's turning into something. And now stopping here, look at the thickness field. It starts to look like there's actually some thermal structure. On the northwestern side, a really intense temperature contrast. There's something to the east. It's about to hit the Iberian Peninsula, Morocco. Let's keep on going. Look at that. We're wrapping some of these thickness fields around. That's actually a warm core. I mean, it's a weak warm core, but it is a warm core. And this is now, let's see, 2016, 12, 8, 4, 0, 1, 2, 3, 4, 5. That's 980 millibars in the middle of that. Let's keep going. The thermal structure relaxes a little bit. We can keep on going. Then it gets tighter again in that same location, this northwesterly side of the storm. And we're going to watch what happens to the thickness field, the 570 decameter thickness line. It's this one right here. Let's see. Very strong horizontal temperature contrast here, and probably strong frontogenesis. I think when we put the precip on there in a minute, you'll see that. There's a cutoff again, 570. Look at how this is starting to take on a clear warm frontal-like structure. Not so obviously yet a cold frontal structure, but boy, there is a strong bent back baroclinic zone across the northwest side of that cyclone. So what is this thing? This is clearly not tropical. They don't look like that. But it's forming at around 25 degrees north latitude. So what is it? Let's keep going. And now we're into forecast mode. This is currently right now. So strong baroclinic gradient on the western side. Here's the warm frontal structure, and then maybe something like a cold front. We keep going. I don't know. That's 570 cutoff thickness. Now let's do a count here. This is 1,000. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's 956 at the center of this thing. And it has a cutoff warm anomaly there. That's the 564 thickness line, that red one right there. So this is a really good time. I like this time especially. Can we go to the precipitation field? I think that's one of the options here. Right there. And 850 temperature. So very heavy precipitation up in this region of the storm. Oh, look at this. These are 850 isotherms. This is occluded. So this thing is a thermal ridge. This one comes back around. So it's only every 5 degrees. I would want to see it every 2 or 3. But I think there's an occluded thermal ridge in here. And that's where the heaviest precipitation is, on the back western side of this thing. And prior work that Andy Hullum, a graduate student of mine, did on these late season tropical transition events, the ones that kind of start out as extratropical storms. I don't know that this one did. I'm not saying that. But those that do, in more obvious fashion, can convert into tropical cyclones, but they only do so after they occlude. Because when they occlude, they get themselves divorced from the vertical shear on top. Because the whole thing gets equivalent barotropic. And once that happens, they can start to take advantage of ASC interaction that might still be pretty robust at 28 degrees north, even in, maybe not in mid-December, but the cases Andy looked at were mid-November. So really, really interesting storm in this case. So that thing is kind of deeply occluded, and heaviest precipitation in the right spot to kind of eradicate the vertical shear and maybe allow ASC interaction to sort of take over. Late in the season though, but boy oh boy, what an interesting storm. We click a couple more times ahead, Pete. Look at that. Isn't that one more back? That is a gorgeous structure, isn't it? Oh man, you just can't believe it that it's like that. Looks so beautiful. Cold front, warm front, and the occluded thermal ridge. I think this is from tropical at the same time. Let's just see what they have, because we can draw a cross section. Let's go forward through the same sequence if we could. Okay, so and they give you a little label there too. So look at consistently the heaviest precipitations on the western side of the storm. And this is, the next one will be 0Z on the 8th, 976, keep on going if you could. And this is now 1,500 thickness, not 850 temperature. 974, here we are at about the current time, and 2 more clicks will be at about the current time. And we're at 964. And look at the thermal structure, just gorgeous thermal structure there. A couple times forward will get us to the 10th, and that's where we had that interesting occluded looking structure. I think it was at 12Z on the 10th. Yeah, so let's take a cross section right through here, just for the fun of it.
It's control, right?
Control, yeah. Perfect. So why I'm doing this, that's perpendicular to the local orientation of the thermal ridge, and it goes pretty much perpendicularly through the warm front. There isn't much of a cold frontal structure, but we get to see what it looks like. Yeah, let's do the frontogenesis in omega first. lots of business. It wasn't like this. Okay, so here's A, so this is the southern portion, this is the Caribbean, and then B is sort of north of the British Isles. It's hard to really interpret this, except with one lone exception. Look at this axis of really intense frontogenesis. I say intense because tropical doesn't care about frontogenesis, let's be honest, they don't. It's not something that matters for tropical storms that much, and so they don't know what contour to use. They go way too high, and you don't see anything until it's a really strong signal. This is a really strong signal, and it goes all the way up to at least 400 milliwatts, and it's on this section right here of the cross section. And then here's the responding vertical motion, which is quite intense, all negative omegas, and then it's supplanted by a little bit of mid-tropospheric frontogenesis, maybe back near the middle of the warm sector of the warm core of that cyclone. So it's a very interesting structure. I'd want to pick this apart myself, not with somebody else making the decisions about how it should look. And then let's look at the PV, just to get an idea of that on this section. So here's the PV. This again, B is the northern side. So here's evidence of that warm frontal structure all the way down to the ground in this storm. And it has its roots in a tropopause fold way up here. Maximum wind speeds in the 80 to 90 knot range. Then a bunch of stalactites hanging down, not any very obvious structure. The one thing I do see though, is you often see a high PV column separated by a low PV column when the storm's occluded. And that actually has to be the case. There's good reasons for that. So that's a really interesting structure, although again, just difficult to make really good sense of it because one would want to fashion one's own sort of look at this thing. But it's definitely worth a look. Very, very interesting storm. And it has implications in the future over the weekend for spinning off when storms occlude. The so-called triple point, the place where the cold and the warm fronts join, is quite well divorced and often to the east of the position of the cyclone center, and that's the case. Can we go back to the surface map, Pete? And just click out of this and you just go right back to it. So yeah, this is the so-called triple point, somewhere in here where the cyclone center has an occluded front coming out, then a cold front and a warm front. So right around here is maybe the triple point. A really sort of unresearched topic that I find quite interesting is redevelopment at the triple point. And I think there's good reasons why that is a preferred spot. But in this particular instance, that redevelopment sends a cyclone, moderate to heavy precipitation across the whole Iberian Peninsula in a day or two in the future from this. I'm not going to show you, you can look at it on your own. But well-developed, well-occluded cyclones can often spawn subsequent developments from their triple points. And I'm not sure I really understand why that happens with the frequency that it does, but it seems to happen. And this instance is going to be a fairly soaking weekend over Portugal and Spain as a consequence. So that's all I have for the discussion today. Are there any well, Pete, you wanted to show this stuff from Dave.
Right.
Well, I wanted to show one other thing, that's the cold pool. I'll do that. So even though we saw it was frigid over Canada, this is the 850 millibar cold pool daily analysis up through December 7th. And for the first time all season, look at this. This is September 1. For on the 7th, on the 8th and the 7th, it was actually about average on the 6th. These are the first 2 days since September 1st. So for the whole cold season that we've been above the average. And we haven't set a record. We're not close to the record. But the first 2 days that we've been above the average for the hemisphere is the last two. Amazing. We were 8th warmest up through the end of November. And then this little burst above the average put us now at 12th warmest through December 8th. So of the last 74 years. So that's still, you know, top 10%, top 15%. But anyway, this is historical for this year. The first time we've been above the average in terms of the areal extent of the cold air pool, and that means colder than normal for the first time. I'm preparing something I want to talk about early in the semester, which is, you know what, September 1 to November 30th is what I call the beginning of the cold season in the Northern Hemisphere. So one can rank by adding up the departure from average for every day. One can rank every single season as, is it one of the warmer years where the departure would be large and negative, or a cold year where the departures added up are large and positive. So you can make a ranked list. Some seasons, the September to November rank position is 40 places different on a list of only 74 from the subsequent December, January, February rank. That really intrigues me. How does the winter change or the cold season change so abruptly? The average change from in the rank list from September, October, November to December, January, February is 16. So having a modest change is not uncommon, but having a change greater than 27 or 28 is a standard deviation above the average. And there are not many such events, but I don't know how to study those yet, because it seems like it's not fair to just compare 3 months to 3 months. Something else, somebody smarter than me about statistics, and that's just about anybody in the room, would probably have a better suggestion about how. But I've identified the events of interest by my simple-minded, goofy way. So I'll show something about that in the spring. So, Pete, why don't you tell us about Dave's thing?
Sure. One of our alumni who visited us, he was talking about some maps that he had been generating on his website of fluxes. Is this right? Amateur hour here. That's not it. Somewhere here, there we go.
There it is, yeah.
So he sent me an email of some analysis of the cold front coming through here last week. And so basically what these are, I think those are so it's surface theta E in the black contours, and then the vectors are surface theta E advection vectors. So red is positive advection, blue is negative theta E advection. And so basically the vectors are pointing in the direction of the wind, and the magnitude of the vectors has to do with the amount of cold or warm advection that you see. So this is starting, is that 0Z on December 1st? No, 12Z.
Yeah, well,
So 14Z, 16Z. So this shows warm advection over us. Cold front's starting to come in through Montana, western North Dakota. And as we get closer to last Friday, you can really see that thing.
that's awesome, isn't it?
So he has these on his website. He sent me an email like 2 days after they were here. It's a very long and not wordy isn't the right word, but there's a lot of information in the email that he sent me, and I haven't really had a chance to digest it yet. But we can make these available on our website, or just links to them if you want to look at these on a more regular basis.
Yeah, it's pretty cool. I first thought it was just the flux of theta E, the velocity times theta E, and then you could take the divergence of that, and one of the things that comes out of that would be the advection. The other would be theta E times the convergence at the surface, which is also kind of an interesting thing to know. But this is not quite that. This is the wind vector direction times the advection. So it's not quite a flux vector, but it's something interesting nonetheless.
If I remember right, it got really windy as that cold advection came by.
Yeah.
That's what you're seeing here with those super long arrows over us pointing out over Lake Michigan.
Yeah, it was brutal. So that's really neat. It's kind of a cool graphical way to look at this.
Definitely.
So.
So anyways, Dave, if you're watching, thank you, or if you watch later. So
All right.
that's what I've got.
Well, thanks, everybody. Next semester, we're going to spice it up. Other people, especially from my group, are going to be doing the discussion, and in addition to me and Pete, will be assisting as always in adding to it. So anybody who'd like to is welcome to give it a try. It's a great experience, and but I thank you for your attention this semester, and Pete, thanks again for driving, and everybody have a good finals week as best as you possibly can.
See you in the spring.